Hello dear students, yesterday we have studied about the reduction of two body problem to one body problem. So as it is a little bit difficult to deal with two body problem, so for simplifying the problem with the concept of reduced mass of the system, we can reduce the two body problem to one body problem. So continuing the previous lecture, in this part we will study about energy change that will take place during the reduction of two body problem into one body problem. So when we change the two body problem to one body problem, there is a change of total energy. So what is the value of that change, because that has to be taken into consideration while solving the problems. So in this article we will derive the expression for energy change taking place in the system on changing the two body problem to one body problem. So consider a coordinate system. Here we have two masses, mass m1, mass m2, and m1 mass is having position vector r1, m2 mass is having position vector r2, and the relative position of mass m2 with respect to m1 is position vector r. So this is the same diagram that we have in the previous article. So as we have studied that center of mass of the two particles lie in between them. So suppose this is our center of mass and it is at position vector capital R from the origin, and it lies between the two masses m1 and m2. So this also we have studied in one of our previous lectures. So position vector of center of mass is given by center of mass is written in short form by Cm. You can also write it by COM, center of mass. So this is a simple notation. You can choose any one of these two. So in scalar form or in magnitude, it is m1 r1, m2 r2 over m1 plus m2. We mark this as equation number 1. Also in a similar way, velocity of center of mass is given by in vector form. It is m1 v1 vector. v1 is the velocity of the first particle, v2 is the velocity of the second particle. So in scalar form we can write m1 v1, m2 v2 over m1 plus m2. We mark this as equation number 2. So applying triangle law of vector addition in this triangle, same order, opposite order, same order, opposite order. So when we apply triangle law of vector addition, according to triangle law of vector addition, R2 is the resultant vector, so which is equal to r1 plus r vector in the triangle that I have just shown now. This one, this one, this one, this triangle. So r, it can be written as r2 vector minus r1 vector. I mark this as equation number 3. So when we differentiate both sides, so r dot, it is r2 dot minus r1 dot. So this is the relative velocity vector of second particle with respect to first particle. R2 dot is V2 minus V1. So we mark this as equation number 4. So in scalar format as well, in magnitude, so we can write as V2 minus V1 by equation number 5. So now as we are to deal with the energy change, so we need total initial energy of the system, then total final energy of the system. Initial system is our two body problem, final system is our one body problem, and then we will see what will be the change in the total energy. So continuing this way, the total initial energy of the system, total energy of the system in two body problem. Okay, initially we have two body system. So for that, total initial energy is kinetic energy plus potential energy, as both the particles are moving with velocities v1 and v2 we supposed. So their kinetic energy is half m1 v1 square, half m2 v2 square. Potential energy is, because both are masses, so it is minus g1 m1 m2 upon r. So this is gravitational potential energy. We mark this as equation number 6. So now we thought of changing the two body problem to one body problem. So two body problem to one body problem. The details is there in our previous lecture, that how we can do it. So on the basis of the previous lecture, we will be using here directly. So it can be done with the concept of reduced mass concept. So it can be done using reduced mass concept, and a reduced mass is given by mu, whose formula is, so what is the mu and what is its relevance? It has been discussed in our previous lecture. So take LCM. So mu is m1 m2 over m1 plus m2. So this is our equation number 7. So using this reduced mass concept system, the two body problem will easily be converted into one body problem. So total energy of one body problem is given by, total energy of one body problem after a reduction is given by E dash. Earlier we used symbol E, now it is E dash. So it is kinetic energy dash, potential energy dash. So now two body has been reduced into one body, whose mass is mu, whose velocity is v square. Whose mass is mu. Gravitational potential energy, it will be same because the same gravitational force will be acting between them. So now we will find the change. Before that we can also substitute the values, or we can later substitute the values, that is your choice. The change in energy is given by, change in energy is given by, so we can say it is delta E, which is 2 body problem energy minus 1 body problem energy. So look at this term, this is same. So when we subtract this term in equation number 8 and equation number 6, this is same. When we subtract, this will cancel out. So actually we will be left with this minus this. So when we write it here, half m1 v1 square half m2 v2 square minus half mu v square. So delta E, it will be half common out of all the brackets, m1 v1 square m2 v2 square minus value of mu, it is m1 m2 over m1 plus m2, value of v, it is v2 minus v1 square. Mu is this one, m1 m2 over m1 plus m2, and v is, we already marked it with equation number 5. So upon solving we will get, take the LCM. So it is m1 plus m2 m1 v1 square m2 v2 square minus m1 m2 v2 minus v1 square. So it will be 1 by 2 m1 plus m2. So when we open these brackets, firstly we multiply these two terms. So it is m1 square v1 square m1 m2 v2 square m1 m2 v1 square m2 square v2 square minus m1 m2 v2 square v1 square minus 2 v1 v2. So 1 by m1 plus m2 we have already taken common. So now we will check what we are left with. So we have simplified all the terms. These two terms will cancel out because two terms in positive, two terms in negative. So what we are left with? So it is m1 square v1 square m2 square v2 square 2 m1 m2 v1 v2. So if we check this, we are left with m1 v1 plus m2 v2 whole square. So this is our change in energy, and to simplify this we multiply and divide by m1 plus m2. So what we are left with? m1 plus m2 this term, we take it forward, and square terms, this one divide by this into this, it will be square of m1 plus m2. So we write it this way. So delta E, it will come out to be half m1 plus m2 capital V square. So what is this? It is a total mass of center of mass. Total mass of system, or we can say center of mass, because center of mass is a point whose mass is equal to total mass of the system. That it is a point where we suppose a body is placed whose mass is equal to total mass of the system. V is velocity of center of mass. So delta E, the energy change, it is nothing but the half total mass, center of mass velocity. So it is kinetic energy of center of mass. So when we reduce the system by changing the two body problem to one body problem, what we are end up with? We are end up with that change in energy is equal to kinetic energy of center of mass. So this is all for today. Keep in touch for next parts of reduction of two body problem to one body problem. Thanks a lot.